Okay. Bismillah ar-Rahman ar-Rahim. So today we are going to continue what we have started. We already know how to find the stiffness for the beam using direct method. So now we want to have two more methods. One is potential and the other one is okay. Before we talk about potential, I think we need to know the stress and the strain. Because then how do you find strain energy? Strain energy is half sigma times epsilon. And everything should be expressed in terms of deflection. Okay? So this is very important now. This is basic mechanics, okay? I know you forget your mechanics, but this is basic mechanics. We need to have it. So, I think we'll, at the end, we say U equal to integral of half sigma transpose epsilon. This is vector, d what? dV. Because half sigma epsilon is the strain energy per unit volume. Okay. Sigma, what's the relationship between stress and strain? Sigma equal to, this is even worse. Okay. Okay, this is even worse. Okay. Let me see. You are lucky, I have a third one. Sigma equal to d epsilon. Always think about this. This is like vector. I don't want you to think about sigma like sigma x. No, you have sigma x, sigma y, tau xy. So always think about it as a vector. But for the beam, we know only sigma x. So this vector will reduce to only one quantity. D, think about it in 1D, it's E, modulus of velocity, but in 2D, there is what? Poisson's ratio, there is a relationship of strain, stress vector to strain vector. So D is a matrix. Epsilon is like a vector. Now, for the beam, what is the strain in terms of deflection? Okay, you have this. And after bending, this is normal. Okay, after bending, it becomes like this. Of course, it goes down. So the strain here, we are talking about this strain. This is called U. You see? The rotation, because now extension here, this is like compression and this is tension. So this is what? U. So how do you relate U to the vertical independent variable? Because our independent variable is the what? The deflection, which is V. So how do you relate V to U? You relate it through here, okay? This is called V, which is what? dV dx, the slope. The slope of the deflection is phi. Okay, how do you relate dV dx to U from the triangle? This is at any distance y, because it's a function of y. At y equal to 0, it is 0. At y in the bottom, it is maximum. So U will be equal to, okay, tan phi or phi, which is equal dV dx equal to what? This distance, which is U divided by minus y, because our y positive is up. Okay? This one here, because our finite element y is up. For beam theory, y is down. So this is negative as far as finite element is concerned. So now, can you find U here? What would be U? What would be U? U will be equal to, you will get a very good relationship for strain. U will be equal minus y dV dx. I think you know strain x is du dx. You see how we go from du dx to dV? Now what it would be? It would be equal to minus y d second derivative dx squared. Okay? Okay. Now can you put it in terms of shape function? Can you put this in terms of shape function? What is V? You should tell me what is V. V is what? N transpose times D. where D is equal V1, V1, V2, V2, and this is the derivative of the shape function. So if you want to take the second derivative of this, comma XX, you understand the second derivative, comma XX means second derivative, right? Equals to what? D is not function of X, so it will be what? N transpose comma X, X, D. This is just to give you some background about the strain. So you can see here now the strain will be a function of the deflection, okay? And the stress is also function of the deflection. We'll come back to the board as we proceed, okay? This is just like warm-up, okay? Do you know the relationship between moment and deflection and the shear and the deflection? Can you tell me? What's the relationship between moment? Because at the end we talk about forces.
Second derivative.
Are you sure?
Yeah.
So the shear will be equal to?
Third derivative divided by EI.
I know this. M over EI, second derivative of the deflection. Is that right?
Yeah.
Okay, what about the shear? There?
Yeah.
So this is X equal
V over EI.
V over EI, like that?
Yeah.
Okay, so once, mashallah, once you know V, you can find the strain. You can find what? The stress. You can find the moment. You can find the shear. One independent variable, which is V, okay? Okay, let's see. This is very important, okay? Now we'll see. Let's see here. It says what we are going to do today is only two things. We'll derive the stiffness using potential energy, and we'll derive it using Galerkin method. We just imagine that we didn't know strain energy. We have to take differential equation. What is Galerkin method? Do you remember what's Galerkin method? You take the differential equation, and then what do you do with it? You multiply it by the shape function, and you integrate, and you equate it to 0, right? Anyway, in case you forget, you will see it, minimization. Okay, do you remember this?
Yeah. Yeah.
This is the potential. This is the strain energy, half sigma times epsilon dV. What is this? This is the work done. Work done on surface load, concentrated load. What is this? Body load, concentrated moment. Yeah, concentrated moment, right? Okay, so this one is just like minus the external work. Just think about the omega is what? The work done with a minus sign. And the work done can be of three sources. It could be due to the applied surface force, which is called traction. This is why they call it T, traction. Concentrated force, which is the nodal forces, or the nodal moment. Okay, dV, what is dV? dA dx. Now, what do you think we will do? We'll just take this and substitute here, pi. Remember that we have everything should be in terms of D. Look, half sigma D, okay. This is very good. This is V, mumtaz. This is also V, good. But this one, where is V here? Because at the end, I want to differentiate with respect to D, right? So how to do it? We have to express stress in terms of strain and strain in terms of displacement, and then multiply them together. Watch this now. Let's go to the next step. What is this now? Can you tell me what is this? This is the work done. You see the traction force, T, distributed load. You see the load here, you multiply by the deflection, which is at the node 1 and node 2. What about MI, M1, and M2? There are three sources. Traction, concentrated forces, concentrated moment. Okay, have you seen this equation before?
Yeah.
You have seen it in the board, right? That the strain is equal minus y second derivative. Okay, very good. Now, what about this? Tell me, what did we do? How do we go? What? So how did we get this strain equal to what? Okay, strain, it's here. You just substitute strain equal to, not this one. Strain is equal minus y, right? Strain is equal minus y, right? Strain equal minus y times the derivative of the shape function, because v equal to n d. So what would be if you want to take double derivative? So v comma xx will be n comma xx d. Now, can you tell me, is this a row or column? D is 4, v1, v1, v2, and what is this derivative? Are you sure row? Yes, row, because this is scalar. It's a row. And this is what? Is it first derivative or second derivative? That's the second derivative of the shape function. So this is dn1 dx squared, dn2 dx squared, and so on. And this is d. So this is now the strain. Can you find the stress from here? You just multiply it by E, right? Okay, this is the stress. Okay. Derivative of the shape function, we call it B. We call it derivative of the shape. Did I say first derivative there? I said derivative of the shape function. I keep it, what? I keep it, yeah, in general. For the truss, it is first derivative. For the beam, it is the second derivative. So B here is the second derivative of the shape function. So sigma equal to D epsilon. MashaAllah, we have now the strain vector like this. Matrix times a column. It will give you a column. Stress will be a matrix times a column. So can we multiply them together?
Yeah. Okay.
We can multiply them together, right? D is E. Even the stress. Is this okay for you?
Yeah.
Other minus Y. BD is the strain times D, which is E. So this is okay. Okay. يلا. هذه أهم خطوة هذه الحين. Substitution. This is the most critical one. I'm not going to go to the next slide. We want to do it together. We want to substitute here. Okay? Let us substitute. Okay, pi. Because once you find pi as a function of D, then you just take the derivative with respect to D. And when I say to D, not the D matrix, the D vector, right? What is the D vector? دقيقة. What is the D vector? What did he say? N1? Is this right? What is it? Reflection. No, the D vector is what is it? V1, V2, V2. That is the D vector, right? It is the degree of freedom. 2 per node. Okay, let us substitute. Yalla. MashaAllah alaykum. You are already knows. Okay, pi. Okay, pi. The right one. Okay, pi equal to. I will put half outside. Integral. Okay. What is this? Oh, we put it. Oh, we put it transpose so that we can put it as a row, right? ها معانا؟ ايش قلت؟ لأن عرفت انك مش معانا. Anything that is transpose means row. Anything transpose means row. Anything that without transpose means column. It means this is row, this is column, row with column scalar. Look here, one. Is it scalar here? How is it scalar? Is it scalar?
Yes, scalar.
Why is scalar?
Because column to row.
Column to row. And here also scalar?
Yeah, scalar.
Okay.
Row to column.
And it is okay. So this is okay, right? Okay. Let's substitute. What is sigma? What's the conclusion? First of all, what is the strain? Can you tell me the strain? Strain vector. What is the strain vector? Minus y d times d. And I think everybody knows d here, right? V1, V2, and okay. What is the stress? minus, what is this? Minus y. Is this d? B. This is derivative, second derivative of the shape function. B. D. Okay, what is the stress? Minus y d b d. But I want sigma transpose because so that I can put it here. Okay, sigma transpose. What will be sigma transpose? You know, in math, when you do, you have to change the order, right? Whenever you have three matrices, multiply by each other and you make transpose, then you make transpose, 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 and you change the order. So you will start with what? Minus y, what? D transpose, B transpose, and D, because it is symmetric. D transpose means D. Scalar. Y is a scalar. The other one matrices. So we don't have to make it transpose. Okay, you want to make Y transpose? Okay. Y transpose. Y will be scalar, right? It's just like alpha. Okay. Now, can you multiply this with that and substitute here? So what should I write here? Minus Y, what? D transpose B. يلا ساعدوني. D. Now, this is all stress transpose. Times the strain. Times the strain. Times the strain. Okay, what's the strain? Minus Y B matrix. What? D. All of this times what? dA dx. dA. Okay, dA dx. Now we have triple integral because we are integrating over the area and over the length. So that's the volume. Anybody knows what is integration of y squared dA? What's the integral? Statics in statics. Integration of y squared dA. What is it called? Integration of y squared dA. It's I, moment of inertia. Look, minus y multiplied by minus y multiplied by dA, and take out of these two and three integrate, take two of them. It will become I. If you take this, with what? With dA, this is, so can I write this as like this? Half integral. Now with linear, okay? So it will be what? D transpose B, B, no, D, B transpose, D transpose B, D, what? Is this transpose?
Yeah.
Okay, transpose, yalla.
D transpose.
What else?
D transpose.
حتى هذه دي transpose is equal to D. Symmetric. وبعدين هاي كمل ايوه وبعدين B. اوكي B وبعدين D وبعدين DX. ما شاء الله. في I هنا بعد؟ I يلا I.
Minus I.
لين تجي بالماينس I هذه؟
Because minus Y.
Yeah, minus y square, right? Okay, good. There is no minus. زين وبعدين؟ Okay, what else we have to do? I think D we can put it E. خلاص. It's E. It's only E. modulus of elasticity relationship between stress and strain is E. وعلى فكرة, if we want to replace this with E, we can put it EI. ما شاء الله. See how we reduce things? Okay. لا ولا بس كذا. احنا نعرف إنه this is all external work. This is external. This is work, and this is work. So this will contribute to the force. This will contribute to the stiffness. It means this is going to contribute to the stiffness. Okay. So all of this term is contributing to the stiffness. But it's not the stiffness yet, because we don't take the derivative of pi with respect to D. Now, take pi with respect to D. Can you take pi with respect to D? What will be? D transpose, B, D, dx. Can you take this pi with respect to D? D vector. It's like D transpose. D is like what? It's like D square. Because this is what? D transpose is row. D is column. It's like you are dotting D with itself. So it's like D square. What is the derivative of D square? 2D. Very good. So when you take the partial derivative, this one with this one with the 2, because it will be D square. So when you take it will be 2, 2 with 2 cancel, and you will have only D here. So it will be what? EI. There is no 2 because it's D square. Okay, integral B transpose B what? Dx and then times dV times D, right? This is your K. This is your stiffness. This is your K. So the only thing you need to do to find K is just to find the second derivative of the shape function and you multiply them together. Can you do this in Mathematica?
Yeah.
If you have B transpose, is this correct? I don't think it's correct, right? Is it correct? Because B transpose is column or row?
Row.
Cannot be row with column, it will be scalar.
Right.
K is a matrix. So what is the mistake? We made a mistake. What is it? أقول لك we made a mistake. What's the mistake?
دكتور we took the يعني derivative of D على في تكامل مش المفروض بس يروح التكامل
لا لا.
يعني كانت جوا التكامل.
When you have D and D here, it's not. This is what it is. It is function of D. Okay. شوف هذه هنا. خلينا نشوفها هنا. Okay. Look at it.
Yeah.
Is it okay? This is what we get.
Yeah.
EI over 2, and there is D transpose, there is D, and B transpose, and B. And we said Y square, DA is I. This is now the contribution to what? To the stiffness. This is contributing to what? To the load, right?
B is square and B is square, so it will be not.
B square, right? B square, are you sure? B square? يلا جاوبوني. B square. B is a vector, right? B is the derivative of the shape function. Okay. Anyway, let's continue. Okay. So this is what you will get. You get this when you take pi with respect to D. We said instead of D square, 2 will be cancelled and you'll have only one D. You see? This D transpose is gone. When you take this with respect to D, the D transpose will be gone. And you have only W with N transpose. Okay. And here, we have P. So what is N transpose here? It should be column. P is a column. But N here is column. Okay? This is column times row. Column times row. This is what? Column. So how many equations here? Four equations. Because N transpose is what? N1, N2, N3, N4. Okay, we got this. What about this one? It will be 4 by 4, right? It will be, this one will be 4 by 4. Yes, 4 by 4, okay? So this is your K. Look at K. EI, 0 to L, B transpose B dx. على فكرة, don't worry. This is in the homework. You will do it. You will go to Mathematica. You know the shape function. You just take the derivative of the shape function. Ask Mathematica to do the derivative for you. Ask Mathematica to do multiplication for you. And you will get what? You'll be surprised to get the same answer. And it says here part of homework number. ما شاء الله. يعني already خارطة الطريق موجودة. Part of homework. Is it homework number 4? ما شاء الله عليكم. يعني you are lucky. 3 or 4? Part of homework 3 or 4? ما تدرون كم سلمتوا ها؟ Okay. Okay. So that's it. Now the idea is, if I give you anything and I ask you to take the derivative of u with respect to d, what you are going to take? This is d transpose and this is d. Can you take the derivative of u with d? What would happen? This is d transpose and this is d. It will be, this is like d square, derivative will be 2d, 2 with 2 cancel, and you'll have only d. And this d transpose will be gone, right?
Yeah.
Just like x transpose x, it's going to be x squared. What's the derivative of x squared with respect to x? 2x. That's it. Okay. Now, I think Galerkin. Wow, Galerkin method. This is the differential equation. Anybody against this equation, this is beam theory. You know it. If you take an element with a load W, you will find that the governing differential equation for the beam is this. Who's taking plate and shell? This seems to be trivial for you.
Yeah.
When you see the differential equation for a plate. Okay? So, how you are going to derive the stiffness using Galerkin method? Procedure. You take the differential equation. Now, of course, you are going to use V as a proximate. And therefore, you take the differential equation, you put it here, you multiply it by the shape function, you integrate over the length, and you get 0. How many equations here? 4 equations, right? Because it's Ni. For N1, it's 1 equation. For N2, it's another equation. For N3, another equation. Okay, do you remember what we need to do? I told you, Galerkin method, what we need to do. There is one thing, keyword. Integration by parts. Integration by parts. Now, do you know why you need integration by parts? So that you can get lower derivative. Because fourth derivative is very, very high derivative. If you go to the shape function, they are x to the power 3. If you take the derivative to the power 4, it will be 0. Right. So you have to use what? From third derivative below, 3 and below. You cannot work with fourth derivative. Therefore, you have to use integration by parts. Okay, do you agree? EI, comma, x, shape function. What is this?
Go to the other side.
Where is it, the other side?
W.
Where is W? Huh? Equal to R? No. My question here, what about this term? W9. H? What?
No, it's the other side.
It says here, let's read. We need only to read. We now apply integration by part twice to the first term. Oh, to the first term. I'm not, this is the second term. The first term is EI, fourth derivative NI dx. The second term is integration W NI dx. So here, all of this is what? Integration by part, the first term. Okay, very good. And then you substitute. You already don't know the shape function. You take, what do you need? You need second derivative? No problem. This is the second derivative. Have you seen this before? Yeah. You've seen it before. Okay. Okay, integration by parts. Look at this W. You see the second one? This is the second term. You see? We brought it back here. Okay, so the first term is giving you these two terms, this one, and this this is the second term equal to 0. Now, do you notice something? Do you notice something here? These are, do you remember integration of u dv equal integration of v du? No, integration of u dv equal uv, and you put the limit. This is uv, you see, and you are putting the limit. This is uv plus the integration of v du, right? Minus, so this is why it's plus the other side. Okay, anyway, this is now, where do you think the stiffness? I think this is load, and you have to realize that the third derivative is moment. What is the third derivative? Second derivative is moment, and the third derivative is shear. You see, that's why we start with this. If you multiply EI you look, if you multiply EI times the second derivative, you will get the shear. And if you multiply EI times the third derivative, you will get what? Moment. Look, we replace with M and V. Okay, moment and shear. Anyway, how many equations? Can you tell me how many equations this? What is in transpose? Is it column or row? N and B, they are column. N is always row. When you make N transpose means column. Okay? Because this is column, okay? All of this column. Okay. So what is the stiffness you think? Where is this stiffness? Anything multiplied by D, stiffness. Can you figure out which one is multiplied by D?
Yeah.
Is this the one?
Yeah.
Oh, do we have it in the board? The one?
Yeah.
Right? Same. MashaAllah. Integration by parts. And then how do I guarantee that you understand the Galerkin method? It means if I give you a differential equation and I ask you, fine, I can give you any differential equation. I can give you differential equation from electrical department. I can give you from any department, from computer, differential equation. And I ask you find, using Galerkin method, find the matrix. How do you find it? I'll give you the shape function. So خلاص? Okay. واضح؟ مش هعطيكم. I will not give you electrical. I will not give you mechanical. I'll give you civil. You only repeat this, what happened here. Okay? شرايكم? You just have to go through this step, and at the end, I want you to get this equation. Look, the derivative of the shape function, you see, 0, 1. The shape function 1 at 0, which means node 1. We know that the shape function at node 1 is 1. What about N3? N3, which means V2. Look, at L, which is node 2, 1. Right? And phi, what is phi at 0? Phi at 0, 1. Phi2 is what? What is the order of phi2? Number 3? 4, yes. You see? Derivative of this is 1. And you just put this in here, and at the end, you get the stiffness. Okay, very good. Now, I think you need to do a problem.
Example, yeah.
You need examples, right? Just one example and we'll finish for today. This is the summary here. Always in the book, there is summary. We want to finish with an example. Oh, we have 20 minutes left, mashallah. So, احنا قلنا ايش? The exam will be on 17th, 19th. Can we postpone it 1 week?
No problem. We will fix the material.
Yeah, until 19, yes. Whatever we cover until 19,
No.
it will be included in the next week. Huh?
No problem, Victor.
Up to chapter 5. Yes, what is chapter 5? Is a frame. Frame, it's very easy. Okay, up to chapter 5. Maybe we'll start with the, we said October or November.
October. October, we said. We postponed 1 week. It will be 16.
Have you seen this equation? Have you seen this equation?
Yeah.
Have you seen this equation before?
The
Okay,
norm.
you remember that. Good. Okay, great. Okay, we want just to see a very simple beam. We want to see how we apply this on a very simple. No, we'll apply, I give you a beam load, find the deflection, find the rotation, find the reaction, find the internal forces, right? Just simple, okay? Yeah, Galerkin method will come in the homework, don't worry. Okay, let's see. Okay, let me see. What shall I do now? Stop sharing?
The example. Said you-
The example is here. Okay, do you have the book?
Yeah, we have it. We have the book.
Okay. Okay. What is this here?
Great. Great question.
This is the next topic. I didn't bring it, you see? So when I say chapter 5, you say, oh, how come chapter 5? Chapter 5 is part of this lecture today. Okay? Because what do you think? Do you think you want to solve using finite element? You can solve finite element using continuous beam, right?
Yeah.
Continuous beam, just like spring. Support here, fixed support here, roller here, and this, and you can add them up. But suppose you have a frame, what would happen? What's the difference?
Global.
Okay, very simple, very simple. If I give you this problem, very simple problem, okay? How do you do that? They're supposed to have smart board here, right? Just by touch, just by my finger, I can draw anything, right?
Right. Should be.
Okay.
Solve it locally then.
So this is fixed, this is like hinge. And I put load here, and I put distributed load here. Okay, and I ask you, yalla, using finite element, solve this problem.
Find it locally.
Well, before we talk about chapter 5, let me see if you know the procedure. What you are going to do?
Stiffness.
Find the stiffness, which is what, 4 by 4? It's gonna be 6 by 6.
The
Why?
local 4 by 4.
Because each node, then each node, now we have space. It might go down. It might go to the right or to the left. So to displacement, you have U and V and rotation. It means that each node has what? 3 degrees of freedom.
9 by 9.
Wow, you have a, huh?
6 by 6.
You have what? 6 by 6. Very easy. If I give you the closed form a K, okay, imagine that I give you 6 by 6. You are going to apply it here. You are going to apply it here, a symbol, and then tell me the size of the big matrix. What would be the size?
9 by 9.
Node 1, node 2, node 3.
9 by 9.
It's gonna be what? 9 by 9? Yes, 9 by 9. Okay. Now what are the degrees of freedom? What are the unknown?
The unknown.
The unknown here, what you are solving for. Out of 9 by 9, you are going to solve for what?
V2, U2 and V2 and
U2, V2,
and 2.
V2, and then what? V3, 4, only 4? Only 4? Huh? ما في only rotation and deflection. Okay. MashaAllah, you are so smart. Okay, to develop the stiffness matrix for the beam with arbitrary oriented plane, not horizontal incline, just like what we did in the truss. Then to develop the stiffness including axial deformation. This is advanced for you. For time being, it's okay. And then apply specific example. Let's see, you'll be surprised. What is this? This is, we have it before, right? Oh, this is not inclined, right? This is local, is the same as the global, right? So what do? We have to make transformation. So this one here is called what? The stiffness for the beam with respect to the local. That's why you see hat. Do you see the hat or?
Yeah.
القبعات هذه شفتوها؟ هذا القبعات الهات. It means local. Now we want global. What do? We make transformation. Okay. Now to make the long story short, do you remember we have an equation in truss? How do you go from local to global? Do you remember this? T transpose K T equal K. This is, you need transformation. You just multiply T transpose K, which is the local, with T. If you multiply these three together, you will get what? You will get the stiffness in global. Okay, what is it?
Where is the T?
Oh,
Where is the T?
this is the T here. 6 by 6. Take the transpose, multiply it by, okay. Huh? Okay. Look at it, look at it. K will be T transpose KT. Okay, let's see now 6 by 6. At node 1, you have D1X, D1Y, Phi1. At node 2, D2X, DTY, Phi2. Okay, if I give you this equation, can you solve this problem now? Easy? Very easy, okay, very easy. Okay, if it is very easy, okay. What about if you want to include axial deformation? How many degrees of freedom? Huh? If you want to include axial deformation,
4.
it will be 4? Really? Still, it will be 6 because the axial deformation, it has 2 components, one in the X and one in the Y. Okay. Anyway, at the end, you will have, this is K, where you include both H. Bending, which means C2, axial deformation means C1, EA, you see? So if you want to neglect the axial deformation, you put C1 equal to 0. If it is only bending, right? But definitely, if I give you this problem, you cannot neglect axial deformation. There is a lot of load here. It would, yeah. Okay. MashaAllah. Look at it here. Very easy, right? Very nice. 6 by 6, right? Very nice. Yalla, yalla, yalla. Example. Look at this example and we'll finish for today. Okay? We have 10 minutes. Okay? As the first example of rigid plane, solve the simple bend shown in this figure. The frame is fixed at node 1 and at node 4 and subjected to horizontal force. Okay, this is the frame. Yalla. MashaAllah. Kam member? How many members? 3 members. How many nodes? 1, 2, 3, 4. 4 nodes. Okay. It's easy. If I give you the 6 by 6, it's easy, right? Is the 6 by 6 global or local? Global or local? Local. خلينا نشوف 6 by 6 local. 6 by 6 local. Okay, let's just see 6 by 6 local. ها لا تغيرون جوابكم ها. Okay. There is S. ايش معنى S؟ اخذته في التراس. What is S؟ أجل global. S means sine theta. C cosine theta. It means this is the stiffness matrix for the beam element rotated in any plane, global. Okay, this is global. There is S, there is C. Okay, very good. So from here, you can program this and you can calculate the stiffness for the 3 elements. Okay. Hey, بس ما في C ولا في S. Okay. بس هذا rotating with respect to X and Y. Okay, can you tell me what is theta here? If this is the global, this is X, and the local is X. How much theta? 90 for element number 1. For element number 2?
0.
For element number 3? Minus 90. Because it's going from 3 to 4. And see, look at the X. This is local. This is global. So the angle here is from global to local is clockwise. Clockwise is negative. عموما find C, find S for each member. This is K1 global. This is K2 global. You have to find C and S. MashaAllah alaikum, you solve for a truss. This should be easy. Only it's more, right? Element number 3, K3. Okay, after that, tell me what to do. Global, you want to add them up, right? خليكم معاي. Is this the one global?
No.
Huh? Is this global or not yet? What is this? This is partition from the global. It is, you told me it is 4 node, 4 times 3, 12 by 12. But you will extract how many?
6.
You will extract only 6. This is the 6. D2X, D2Y, and Phi2. This is for node 2. For node 3, D3X, D3Y, Phi3. Because it is 1 is fixed and 4 is fixed. Can you solve for this 4 and 6 unknown? Yes. Go and find the forces. And after finding the forces, did you take CE 511? Who took 511? This should be straightforward. Yeah, this is a review for you. You found this. Now, how do you find the shear and the moment for each element? And we'll finish the class for today. Now you have everything. What do you do? Suppose now you have D2X, D2Y, Phi2, D3X, D3Y, Phi3. How do you find the internal forces? Which matrix? No, not the larger. Not the larger. The 6 by 6. When you solve the big matrix and you extract from it, these are the displacement with respect to the global. You have to convert it to local. And you take local, you multiply it by the local stiffness to get the local forces, which is shear and moment. See the steps here? This is global. Okay. Now, from here, if you answer this question, we will finish for today. For member number 1. Member number 1 is vertical. Okay? It's like this. Where is node 1? Here. Node 2 here. Now I want to know the shear and the moment here and the shear and the moment here. At node 1 and node 2.
Put the displacement we got.
Do you know the forces? What are the forces at node 1? I think shear, axial force, and moment. Shear, axial force, and moment. These are the 6. 1, 2, 3, 4, 5, 6. Okay? Now, you have to find K local, which is 6 by 6. You multiply it by the D.
Yes.
And that will give you the forces. Can you order this? What are the forces? Assume this is node 1 and this is node 2. What shall I write here? It will be what? F1x, which means shear. Is it? Is it F1x shear? No, because x is always parallel to the axis. F1x will be axial. F1y will be shear. And Phi1, you see? So this one will be this one here, you see? F1x will be axial force. F1y shear. Okay? And the other one is Phi. Now, what about the other one? The other node? Axial force, shear, and Phi. ما في displacement. V shear هذا shear force هذا مو V. V shear force مش V مو displacement. هذيك small V. ها؟ صح خطأ أنا أخطأت. Moment. مضبوط moment. Yes, thank you. والله ما شاء الله عليك أنت الصاحي. Where is it? Moment. وين moment؟ الفي حتكون هنا صح؟ مضبوط. ما يقول لكم إلا كافي شوب هنا before you start, right? You cannot without coffee shop. It's serious, really. Okay. ما تعشيتوا لسه. You haven't had dinner yet. It's really this C570 is torture, right? عذاب. Huh? No, there is the people taking transportation. This is why we change it. The best thing is that you sleep before you come to the class. You have lecture? Sleep before the lecture. We have work. Sleep at night. Sleep at night. Okay. Look here. These are the displacement. Okay. You take the look. After you do this, this is how it would deflect. It will be like this. Okay. The rotation here will be positive, negative. You will see phi2 is negative clockwise, and you will see this one also negative. And you will see it's something like this. MashaAllah. Then ايش نزيد؟ اذا قلتوا لي هذه يلا ايش هذه؟ ايش هذه؟ You're transporting what? Transforming what? تاخذ الجلوبال, because the answer that you get global, you multiply it by the transformation, that will give you D local. You see? D local. At node 1, it is 0, 0. Fixed support. No displacement. You see? These are the three. 1, 2, 3. This is node 1. Look at node 2, which is at the top. How much the displacement? This is in the X. This is in the Y. And this is the rotation. Rotation is negative, clockwise. That's how I draw the shape from these. Yes. Yeah, elongation, exactly. Local, everything is local now. These are the, now how do you go to the shear, and we'll finish. How do you go to the shear and the moment and this? If you want to draw shear and bending moment diagram for member number 1, you take those displacement, which is in local, you multiply it by what? K, which is the local. Okay, let's see if he multiplied. Ya Allah. This is the local K. This is the local displacement. It will give you what? Local forces? Okay, let us see the local forces. هذه local forces. يلا. If you can draw these forces on member number 1, معناته ما شاء الله عليكم, you master it. يلا. What does it mean, these forces?
1x, we have.
يلا. Now I will draw member number 1. Now everything with local. Local means what? I think it's going up like this, right?
Yes.
So this is node 1, this is node 2. Okay. The first 3 is at node 1. What do you think this one?
Normal.
X. Is it down or up?
Down.
Down, because it's negative, right? How much? 3,700. لازم يكون in equilibrium. Okay, we finished the first one, which is axial. The second one, shear. Is it to the right or to the left? Is it right or left? Left, because the global, it was like this, and now it is X, and this is Y. You see, you make rotation 90. So positive Y is in the left. So this is the shear. How much is that? 4990. 4990. Okay, وبعد ايش؟ مومنت هذا؟ زي هذا المومنت 376,000. Is it clockwise or counterclockwise? Counter, يعني زي كذا؟ كم 3 7 6 376 zeros.
Yes.
And then okay, go to the other end because I want to see if it's in equilibrium. Now in node 2, the first one is what? Up or down? Up. How much? And هذه واضحة ان it is already summation of fx equal to 0. Very good. Now let's go to y. Are you sure?
Yes.
It has to be to the right. Okay. 4. Is it 4? 990. Okay, moment. كم المومنت؟ 223,000. Is it clockwise or counterclockwise? Counter? This is clockwise.
Correct. Go ahead.
If it is positive, it means counter. This is positive counter. This is positive counter. So this is 2, 3, 2 what? 2, 2, 3? 2, 2, 3 what? 0, 0?
Yes.
Only 2 zeros?
0.
0. Do you think this is an equilibrium? I know, summation of fx 0. Summation of y 0. Okay, take the moment here. Do you think it will be 0? It has to be 0. It will be 0. It will be 0. A frame is in equilibrium. Part of the frame should be in equilibrium. Yalla, when the calculator? Take this. It is equal to this. 376,000 positive. Okay. Right? Plus 223 positive. Minus 4990 times the height. Height? The answer divided by the height, it will give you. See the height. Okay. علشان تقدرون تنامون الليلة so that you can sleep tonight. Okay. How much the height? Because really the height, that will make it. It will be too much, the height. Okay, the height. Okay. 10 feet times 12 inches. You see how much the height? It will be 0. It will be 0. Yes. Now you can draw shear bending moment diagram. خلاص, and I promise you until 11. Okay. I have to stop now. Okay. Very good. Stop share. Stop recording first. والله هذا السيكونس شوية